So today what we're going to talk about is differentiability and how a derivative might fail to exist. And then we have names for certain conditions that happen, okay? And we're going to go over like, okay, this, when it's not differentiable, it's called, this is the reason why, because in this case, and we're going to be talking about a corner, okay? So what is a corner, all right? So what happens here is it is not going to be differentiable right here at x equals 3. This is called a corner because all of a sudden, the tangent slope automatically changes from being one value to the next value. And we can show that, all right, by taking the one-sided derivatives, okay? So if we want to take the limit as h approaches 0 from the right, so this would be a right-hand derivative, okay, of f of 3 plus h minus f of 3 all over h. If we did the right-hand derivative, okay, so right here's where that's the anchor point. That's where we want to find the derivative at. And we pick another point, that's the plus h part, would be to the right of it, okay, because h is positive here, okay? And we bring that point in. All the lines drawn between these 2 points, any point you draw is always going to have the same slope. In this case, the slope would be 1, okay? So this is, in this specific case, it's equal to 1, all right? If we take it from the left hand, okay, again, this is the anchor point, and we pick our other point over here, and we got to write the same thing because that's the derivative, 3 plus h, okay? That's the definition. So the limit as h approaches 0 from the left of f of 3 plus h minus f of 3 over h. Okay, so if we do this one, all right, this h is actually a negative value. So that causes it to go to the left, okay? And so that's this second point away from the anchor point at 3 is going to be on this left side, and we're going to bring that one in, and that slope would always equal -1, okay? Now, what happens is one of these comes out to be a number. This is how you know it's a corner. One of these will come out to be a number value, like, 1. And the other one is a different number. So we can write, okay, so one of these is going to come out to be a number value. And then what can happen is the other sided derivative will come out to be a different number or infinity. So one of these could, not both of them, but one of them could come out to be infinity or negative infinity. And when that happens, we say there's a corner, and we say there would be a corner at x equals 3, and we would say f of x is not differentiable at x equals 3. Some people call this a kink in the graph, okay? So a kink is like a quick bend. Anytime you have a quick bend, then that's called a corner, okay? All right, let's go to the next one. So for this next one, okay, it's not going to be differentiable at this value right here, okay? And this is I call it the bird equation. It kind of looks like a bird, right? How you draw a bird when you're a little kid, and you draw it like that, right? It kind of looks like that, all right? That when you see that, that's called a cusp, okay? And what happens on a cusp is if we take the limit as h approaches 0 from the right, and we're going to do it at -2. So this is f of -2 plus h minus f of -2 all over h, okay? So here's the point we're trying to find the derivative at. If we pick another point to the right, it's going to have positive slope. This side's going to have positive slope. And as we come in and in and in, right? And what's going to happen is there's going to be a vertical tangent right here. So what happens is on this right-hand side, this comes out to be positive infinity in this case. All right, because there's a vertical tangent in there. Now, if we come from the other side and if we draw a line between this anchor point and the other one, we would have a negative slope. So let's go ahead and write the left-hand derivative, which would be the limit as h approaches 0 from the left of f of -2 plus h minus f of -2. Okay, and if we try to find the derivative right there with another point on the left of it, and we bring that point closer and closer and closer, okay, as we get closer, that slope between the 2 points is going to be negative. Well, what happens right here? Well, it goes vertical, right? So you can't determine if it's positive or negative right when it goes vertical. What happens right before it, though, is the slope was negative. So what happens is this comes out to be negative infinity. And we can go through all the work and show that it's either going to come out to be infinity or negative infinity, all right? But this is going to, what happens is what makes the corner is that these are going to be opposite infinities. And that's what's important here, okay? Not the calculation of the one-sided limits, okay? So right here, okay, what causes us to call this a cusp is these are opposite infinities. So what will happen, and this is how you know it's going to be a cusp, is if one of the one-handed derivatives comes out to be positive infinity and the other one-handed derivative comes out to be negative infinity. When that happens, you know you have a cusp, okay? All right, so we would write, after we do all the work to show that one's infinity and one's negative infinity, okay, we would show that there's a cusp at x equals -2, and we would say f of x is not differentiable at x equals -2. So one of the things I want you to do, all right, is I want you to be able to look at a graph and just look at the graph if I give it to you and you say, oh, there is a cusp right there, or there's a corner right there, okay? All right, so let's go to the next example. So this next one is a vertical tangent, okay? And it's not going to be differentiable when we have a vertical tangent, okay? So if we look at this one's going to happen right here, right there at x equals 2. So we need to do the right-hand derivative. So the limit as h approaches 0 from the right of f of 2 plus h minus f of 2 all over h. Okay, so we pick another point on here, and if we bring that point, if I'm trying to get you to visualize this. If we have a point like right here, and I draw a line between where I'm finding the derivative and that point, and I bring that point in, do you see how it's going to be going vertical right here? As I bring this one closer and closer and closer, the line between the 2 points is going to get closer and closer and closer to being vertical. What is it if I do a point like right here and connect these? Well, that you see, that would be a positive slope. So as we bring this point in, that's always going to be a positive slope between the 2 points. So right when it goes vertical, what that means is this is going to go to positive infinity. All right. And then let's take a look at the limit as h approaches 0 from the left. So this would be the left-hand derivative of f of 2 plus h minus f of 2 all over h. Okay, so here's where we're trying to find the derivative at. I'm going to pick a second point because h is negative. That's going to cause me to pick it from the left-hand side. That's why this is called a left-hand derivative. If I draw a line between this point and a point on the left, like right here, then that's going to have positive slope. If I bring this point in and draw the line between them, it's going to have positive slope. If I get this point closer and closer and closer, positive slope. And then so that I'm going to be able to tell right when it gets on top of this point, right before it, it was a positive slope. So what that means is this is going to be a positive slope. So this is going to equal positive infinity. And what makes a vertical tangent is that these come out to be the same infinities, both positive infinity or both negative infinity. If that happens, then what we say is there's a vertical tangent right there. So these are the same infinities. So same infinities, vertical tangent. Opposite infinities, cusp. Opposite number values, corner. One number value and the other one being infinity or negative infinity, that's also a corner. Okay, so people have a lot of times people have a tough time with the difference between a corner and a cusp. Okay, and that was, let me go back to it. All right, so the difference between a corner and a cusp these both have to be opposite infinities, and for this one, one of them can be infinity only. All right, one of them has to be a number, and the other one has to be some type of infinity. Okay. All right. So you could have something like this that comes in like this, and then this side would have a slope, okay, a negative slope, and then you could have one like this, and that would still be called a corner, even though this side would have a vertical tangent and this side would be have a number value. That would still be considered a corner. Okay, it's only a cusp when they are opposite infinities. You know what? I should have told you guys this function right here. So functions to look out for, okay, is something like this. F of x is the absolute value of x minus 3 and then plus 2. So absolute value functions, you're going to have corners. Okay, so anytime you see absolute value function, corner. All right. Cusp, this function here was f of x is equal to 2 times x plus 2 to the 2/3 power minus 3. Okay, so this is one thing that's going to happen when the denominator is an odd number and the numerator is an even number. That's going to cause a cusp to happen. Okay, there's other reasons of cusp, so I wouldn't just rely on that. Okay, but that is one specific function that you will have a cusp when the exponent is a fraction and the numerator is even and the denominator is odd. You're going to have a cusp. Okay, because basically what it is it's the cubic function, but this side, one side has got flipped up over where the vertical tangent was. Okay, so if you, for instance, if you were to take this part right here and flip it up, you would have a cusp. Okay, and one of them would be infinity, and one that would cause them to be opposite infinities if you did that. Okay, all right, and then this one is f of x is equal to x minus 2 to the 1/3 power. This is cube root, okay, because 1/3 power is cube root, and then minus 3, okay, which could be also the cube root of x minus 2 minus 3, like that. All right. Now, so those are the three one-sided derivatives that will cause us to not be differentiable. And I should say this, okay? So we say a vertical tangent, this one, because they're the same infinities, we'd say there's a vertical tangent at x equals 2, all right? And so f of x is not differentiable at x equals 2. Okay, you could say f of x is not differentiable at x equals 2 because there's a vertical tangent at x equals 2. Okay, you could say something like that. All right, let's go to the next one. So the next rationale reason why we can't be differentiable is any type of discontinuity. So this relates back to what we learned the last unit. Okay, so any type of discontinuity, if you have a discontinuity, it's not going to be differentiable. So the discontinuities are removable discontinuities, otherwise known as holes in the graph. Okay, jump discontinuities, infinite discontinuities, or, and this one's not going to be tested, okay, but oscillating discontinuities. Okay, so in this case, we would say it's not differentiable at x equals 2 because there is a jump discontinuity at x equals 2, okay? So there's in this case, there's a jump discontinuity at x equals 2. So f of x is not differentiable at x equals 2. Okay. And so that would be enough to say, hey, it's not different. This function is not differentiable here at this value. Okay. Now, this is not a hole. Okay. This is just an open dot. Okay. So it's not a hole. So don't think every time you see an open dot, oh, hole. Okay. This would have to be connected for there to be a hole. Like this one, if we slid this one down all the way to right here to the point 2, -4, then, it was just one little piece, one little hole right there that was missing, then that would be a removable discontinuity, okay? So this isn't the hole. Please don't think every time you see an open dot, oh, hole. No, okay? That just means this function, the value is down here for the function, and then right to the right, it jumps up to right here, right to the right of this open dot. Okay, so how do we show continuity? So quick review, okay? We have to show the function value, we have to show the limit, and to show the limit, we have to show the one-sided limits, and then we have to show that the function value and the limit are the same. That's how we show it's continuous, right? So to show a jump discontinuity, we have to find f of 2. So f of 2, well, it would be -4 because that's what it's defined as because of the closed dot. That's how I knew that. So this is equal to -4. We have to find the limit as x approaches 2 of our function f of x. But to do that, I need to do the limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. So from the left of 2, that would be -4. To the right of 2, as you come along the function, that's gonna get closer and closer to being 1. And that's what's causing this to be called a jump discontinuity. The one-sided limits are different, okay? Which means the limit as x approaches 2 of f of x does not exist, or DNE, okay? And then we would say, all right, so the third part, this is the first part, this is the second part, and the third part would be the limit as x approaches 2 of f of x does not equal f of 2. If we showed all three and all three were true, then there wouldn't be a discontinuity. It would be continuous at that x value, okay? So I just wanted to go through a quick review of how do you show that there's a discontinuity at an x value on a function, okay? And that's how you show it. You guys make those 3 statements, all right? Okay. So let's do an example now, and then we'll call it now. We haven't done this yet, but we're going to call it what it actually is. Okay, so let's do that example next. Okay, so looking at this problem, all right, here's a function. It's made up of 2 different pieces. Okay, I haven't written as a piecewise, but it could be written as piecewise. To the left of x equals 3, it's this parabola or quadratic function, and to the right, it's the square root function, and they're connected right here, so it's continuous. So we don't have a discontinuity, so we don't need to say, hey, it's not differentiable because of a discontinuity. It is continuous, okay? Now, looking at this, we should start to realize that if we do a left-hand derivative, we are going to get a number value, right? Okay, you can kind of see like the slope would be somewhere right in here, and that would be a numeric value. But on the right-hand side, as we come in, you can see that this is flattening out right here. So if I drew 2 points and got closer and closer, we would have a slope that would be vertical, right? Or tangent that would be vertical, which means this right-hand derivative, and right before it went to vertical, it had a positive slope. So this right-hand side is going to go to infinity. Okay, so now we're going to show this, all right? But I wanted to like look at it and have a visual and have an understanding, a conceptual understanding of what I should be getting at the end of this. Okay, so the right-hand derivative, I think I'm going to get positive infinity. And the left-hand derivative, I'm going to pick up and get some type of number. Okay. All right, so let's go ahead and do both the right-hand derivative and the left-hand derivative. So the right-hand derivative would be the limit as h approaches 0 from the right of f of, and we're going to show that's not differentiable at this point p. Okay, so f of 3 plus h minus f of 3 over h. Okay, so that'd be the limit as h approaches 0 from the right. If we put 3 plus h into this function, okay, now h is to the right of it, so at 3 we're at this point right here. Okay, so what I'm trying to say is this number right here is bigger than 3, so that tells me to pick the one that's on the right, this function. Okay, so this would be the square root of 3 plus h minus 3 plus the 4, okay, and then minus f of 3, and that would be 4. And you know what? I should have put brackets around that. All over h. And so this is equal to the limit as h approaches 0 from the right. Well, right in here under the square root, that would be 3 plus h minus 3, or just the square root of h. And then we have plus 4, and then we have this minus 4, all over h. Okay, so this becomes the limit as h approaches 0 from the right of the square root of h over h. All right, so let's try direct substitution, right? Well, we get 0 over 0, right? Okay, so how can you handle this? And we have to go back to exponent rules, okay? So this becomes the limit as h approaches 0 from the right. Okay, the square root function, a square root is really an exponent, and the exponent would be a fractional exponent, and for the square root, it would be 1/2. So this is h to the 1/2 over h to the first power. Okay, because I was able to write both of these in exponents, I can use exponent rules. So what I'm going to do is I have h to the power divided by h to the power. We're going to subtract these powers. So this becomes the limit as h approaches 0 from the right of h, and 1/2 minus 1 would give you negative 1/2. Now, what does the negative exponent mean? Well, it means 1 over h to the positive 1/2. So this becomes equal to the limit as h approaches 0 from the right of 1 over h to the 1/2, which h to the 1/2 is the square root of h. So this is equal to the limit as h approaches 0 from the right of 1 over the square root of h. Okay, so now let's try to do direct substitution, because I'm going to get 1 over 0. Okay, so that tells me it's either going to be infinity or negative infinity, but which one? Okay, just before h is 0, because we can't tell when h is 0, but just before h is 0, h was positive. So what happens is this is going to become a number that's really close to 0, but it is positive, okay? So what makes that is a positive 1 divided by a really, really small positive number. And so that's going to tell me it's going to come out to be positive infinity. And that's what I said earlier. If we use this as an anchor point and we bring another point in and look at what the tangent slopes are right up until we get the point on top of the other one and it becomes vertical, right before it was vertical, we had positive slopes, okay? And that's why this is coming out to be positive infinity. All right, let's do the left-hand side. It's going to be a little more algebra, okay? All right, let me slide this up a little bit. I'm not going to run out of space, okay? All right, so the next one is the limit as h approaches 0 from the left. Please, 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 again, I'm going to say this, and I meant to say it earlier. Please don't write this is f prime of 3, because that would be wrong. F prime of 3, we can only write that when both of these exist and they're the same number, okay? All right, so the limit as h approaches 0 from the left of f of 3 plus h minus f of 3. And by the way, I know f of 3 because it's this point right here. The output is 4, okay? So this is equal to the limit as h approaches 0 from the left. Okay, 3 plus h, all right? Our h, because it's approaching 0 from the left, our h is actually negative. So we're adding a negative value, which actually makes this smaller than 3, which makes it to the left of 3, which means we're going to use the quadratic, okay? So this becomes, and I'm going to use a bracket here, 3 plus h squared minus 6 times 3 plus h plus 13, and then close my bracket, and then minus, and we already know f of 3, okay, just from right here, it's 4. All over h. Okay, so this becomes the limit as h approaches 0 from the left, I almost said right, of, and this becomes 9 plus 6h plus h squared. And this becomes minus 18 minus 6h plus the 13, and then minus the 4. All over h. Okay, this is equal to the limit as h approaches 0 from the left. And then here we have 9 minus 18, that's negative 9. And then negative 9 plus 13 would give you 4. Okay, so we have 4. And then we have 6h and minus 6h. Those are going to cancel. And then I have the h squared here, right? So plus h squared. And then minus the 4. All over h. Okay, and then that becomes the limit as h approaches 0 from the left of h squared over h, which becomes the limit. That's exponent rules again, right? It is, right? It'd be 2 minus 1, which would be 1. So this would be h to the first, or just h. So this becomes the limit as h approaches 0 from the left of h. Okay, now whether it's left or not or right, it doesn't matter, because now we can do the direct substitution, right? This becomes 0. Okay, so how do we know it? This is classified as a corner. How do I know it's a corner? I know it's a corner because the right side is going to infinity and the left side is going to a numeric value. Okay, the left, I shouldn't say right side. Okay, the right derivative is approaching infinity and the left derivative is 0. One's infinity, one's a number. That means it's a corner. Okay, if these had both come out to be infinity, vertical tangent. If they had come out to be opposite infinities, cusp. Okay, and then that's it. It's a corner. The right hand and the left hand derivative only needs to be done for a corner, a cusp, or a vertical tangent. Okay, other than that, it'd be a discontinuity, and that's why we would just go through that process. We wouldn't have to do the right and left hand derivatives. Okay, so we would say f of x is not differentiable at x equals 3 because there's a corner at x equals 3. So it's not differentiable here. Why, the corner part, and where is that corner? The corner is at x equals 3. Okay? All right, guys, that's differentiability. You know, we only have one more day in this unit, guys. One more day. So that's going to be Friday. All right? So I'm going to give you guys a worksheet for today to work on and to do that. Okay. I think I have 4 problems on the worksheet for you. Okay. All right, you guys, have a wonderful day. Take care. Bye.